Okay, ladies and gentlemen, this is lecture 31. We're going to cover most of section 5.3, which is about a specific kind of random variable called the uniform random variable. So let me get started by pulling up a whiteboard. So this is section 5.3, the uniform random variable. Okay, so this is going to depend upon two parameters. So two real numbers, alpha and beta, real numbers. Alpha is less than beta. And what we do is we draw the picture of the PDF for this first, and then it'll be clear what's going on. So maybe alpha and beta are over here. They could be negative, but alpha is less than beta. And now we're going to look at a rectangle of area 1, because it's got to be a PDF. That means that the height has to be 1 over beta minus alpha. So that tells us that f of x must be 1 over beta minus alpha if alpha is between x and beta, and 0 otherwise. So this is a probability density function, and we will say that a continuous random variable x is uniform of type u alpha beta. U alpha beta refers to the u refers to uniform. The alpha and beta refer to the parameters. If its PDF is as above. So that's the definition. And what I'd like to do is compute, first of all, the cumulative distribution function of this random variable. Okay, so what's the CDF? Of x of type u alpha beta? That's the first question. Okay, so now remember the definition. By definition, f of a, the cumulative distribution function, is the integral from minus infinity to a of f of x dx. So I think it makes sense to look at the picture of the graph again. Here's alpha and here's beta. Okay, so now what's going on? So it depends where x is, where a is. So if the number a is less than alpha, then there's no area under the curve, because the curve is supported between alpha and beta. And so here's my rectangle as before. And so you're going to get 0 in that case. What happens if a is greater than beta, or greater than or equal to beta, maybe I should write, less than or equal to alpha. If a is bigger than or equal to beta, then a would be out here. You're picking up the entire area of the rectangle, so that would be 1. So what happens if a is between alpha and beta? Well, a would be somewhere here, and the area you're picking up would be the green shaded region between alpha and a. This would be the integral from alpha to a, but it's the area of a rectangle, and so it's going to be given by a minus alpha, that's the height, the base, divided by the height, which we know to be beta minus alpha. So that's what f of a is. Okay, so that's cool. So we've computed it. Okay, so now what I'd like to do is compute the expectation and the variance of the uniform random variable. And so let me do that. So let's talk about expectation first. So let x be a continuous random variable be of type u alpha beta. And so what is the expected value? So e of x is the integral from minus infinity to infinity of x times f of x dx. That's the general definition, of course. But now we note that everything is supported between alpha and beta in the integral, and f of x is given by 1 over beta minus alpha in that interval. So now the 1 over beta minus alpha is a constant, and we're integrating x, so you get x squared over 2, and it's from alpha to beta, so you're going to get 1 over beta minus alpha times beta squared over 2 minus alpha squared over 2, so it's beta minus alpha squared over 2. And beta squared minus alpha squared is beta minus alpha times beta plus alpha, so you're going to get alpha plus beta over 2. This is the midpoint of the interval from alpha to beta. This is the midpoint right here. Alpha plus beta over 2. So that's what the expected value is in this case. Okay, so we got the expected value. Now I want to compute the variance. That's going to take a little more calculation. In order to calculate the variance, what I'd like to do is calculate the second moment first, and then we'll use the usual formula that relates the variance to the second moment. Okay, so let's talk about e of x squared on this slide. So that would be the integral as before. You're integrating from alpha to beta. That's where everything is supported. 1 over beta minus alpha, that's the PDF times x squared dx. And you're going to be left with 1 over beta minus alpha, x cubed over 3 from alpha to beta, which is going to give me 1 over beta minus alpha times beta cubed minus alpha cubed over 3. So now what I'd like to do is note that, let me do it up here in the corner, that if I take x cubed minus y cubed, it's x minus y times x squared plus xy plus y squared. This is a factorization of x cubed minus y cubed. How do you get this factorization? You can long divide x minus y into x cubed minus y cubed. So what this tells me is that the expression I have over here is going to be given by alpha squared plus alpha beta plus beta squared over 3. So therefore, if I want to compute the variance, I'm going to get this expression, alpha squared plus alpha beta plus beta squared over 3 minus my expected value quantity squared, which was alpha plus the midpoint squared. And a little algebra has to be done here, but what you'll end up having at the end of the day is the length of the interval is beta minus alpha squared over 12. That's what you get. So let me box that off. That's a cool result also. All right, so we've computed the expected value or the expectation and the variance. Okay, so we're going to end this lecture today with doing just a simple problem directly from the text. The uniform random variable is sometimes applied in situations where you have waiting times for something to occur. So for example, Old Faithful, the geyser, it erupts every 91 minutes. And suppose you arrive there at a certain time, how long would you expect to wait, right? So things like that. So let me do an example from the text though, example 3C. 3C goes like this. You have buses arriving at a bus stop. At 15-minute intervals. So say starting at 7 a.m. So in other words, 7, 7:15, 7:30, 7:45, etc. Okay, so now you arrive at the bus stop, at a time uniformly distributed, which means we're going to be using the uniform random variable sometime between 7 and 7:30. Okay, and then what we have to do is, the problem is saying find two things. Find the probability that you wait less than 5 minutes for the bus to arrive. And then find the probability that you wait more than 10 minutes. Okay, so here's the deal. We're between 7 and 7:30. We're uniformly distributed. So so if we think of 7 a.m. as time 0, we have a 30-minute interval. So this is U0 30. The alpha is 0, the beta is 30. And we're asking for waiting. Now a bus is going to arrive every 15 minutes. So a bus will arrive at 15 minutes after you arrive, within 15 minutes of your arrival for sure, right? So let's let X be the random variable given by the number of minutes past 7 a.m. that you arrive. Okay, so you arrive at a certain time after 7, and we know that this is a random variable of U0 30. Okay, so what is problem A asking? Problem A is asking for the following. You want to know whether you're waiting less than 5 minutes. The only way you could wait less than 5 minutes is if you arrive 10 minutes after 7 up to 15 minutes after 7. So you would arrive in this range, or you could arrive in the range from, so this is from 10 to 15, or from 25 to 30, so 25 minutes into the half hour, I should say, right? Because then you'll have less than 5 minutes to wait, right? So you arrive after 7 o'clock. When do you wait less than 5 minutes? Well, this is the only possibility. There's less than 5 minutes in these two blue intervals. So we're interested in knowing the probability that 10 is less than X is less than 15, plus the probability that 25 is less than X is less than 30. That's what we have to compute. Now that's easy to compute with the uniform PDF, because it's the integral from 10 to 15 of 1 over 30, because remember f of X here in this case is 1/30th, according to the formula. It's 1 over B minus A, right? Inside the interval. So it's 1/30th dx. So that's going to be, and then we're going to have to add to it the probability, the integral from 25 to 30 of 1/30th dx. And so this gives you X over 30 evaluated from 10 to 15 plus X over 30 evaluated from 25 to 30. And you can compute this and you'll get 1/3. So 1/3 is the answer for part A. Okay, well, what about part B? I'll do that on another slide. Part B is we're asking waiting more than 10 minutes. So let's draw the picture again. So here is every 15-minute interval. So what does it mean to wait more than 10 minutes? It means that you arrived within the first 5 minutes, or you were from 7 o'clock, or you've arrived within 5 minutes of 7:15. So this is the region in question. So it's the probability of x between 0 and 5 plus the probability of 15 less than x is less than 20. And you can compute that as well, and I'll spare you the details. You'll get a third. Same kind of argument. Okay, that's all I wanted to do today. This is the uniform random variable, and we have not finished this section. This is section 5.3. We will continue with 5.3 next week.